Hi there. If you're into restoring old receivers or old radios and restoring old guitar amplifiers or even building amplifiers, you probably find this information rather interesting. So those orange dip, brown dip, green dip, and those little yellow axial leaded capacitors, and many more capacitors, have a polarity in circuit and should be installed in the circuit the correct way in order for them not to pick up hum from adjacent parts of your amplifier or radio, or to pick up interference from adjacent parts of the chassis, whatever they're installed into. So in this video, what we're going to do is we're going to discuss why these capacitors have a polarity, and then we're going to build a little circuit that will help us locate this polarity quickly. We all know that if you're restoring an old radio or an old guitar amplifier, they usually have a handful of capacitors in them, and you really don't want to be doing this while you're restoring the receiver or amplifier. So we're going to build a little circuit that'll help you grade them with an oscilloscope very quickly, and then with a little felt marker, you can mark the band end, or as it was called in the old days, the outside foil end of the capacitor. So let's get into the video and start discussing why these capacitors actually have a polarity. Here we have two very common circuits that you'll find in a lot of vacuum tube gear. This upper circuit here you'll notice is in a lot of guitar amplifiers or high fidelity amplifiers or stereo receivers. This really is just an audio amplification chain here. This bottom portion of the schematic I've kind of drawn to represent either an IF amplifier or an audio amplifier. Of course, we'd have to amend this transformer to represent either or, but we're not going to get too crazy about that right now because it's all about just learning which way we need to install our new capacitors in this circuit for the best circuit performance and the least amount of interference. So way back in the day, they used to make capacitors that looked like this. And if you ever find a capacitor like this in any kind of gear that you're working on, it has to go. These are all faulty by now, and they leak. Now, when I talk about leaking, I don't mean that they leak physically. They're not leaking a substance like oil or goop out of them. They leak DC across them. So whenever you hear the term leaky capacitor, that means that they're leaking direct current through them. Capacitors are supposed to block DC and pass alternating current through them. So when they leak, that means that this capacitor is effectively turning into a resistor, and that is no good for the next stage. So what happens in these capacitors is they've got paper inside of them that's gone acidic, and it's basically just turning into a big resistor right now. And when these capacitors turn into resistors, they bias up the next stage and cause the tube over here to draw heavy current, and it causes damage to the circuit. You burn out plate resistors and IF transformers, and it does all sorts of bad things. So you want to get rid of these capacitors and replace them with a modern equivalent like an orange dip or a brown dip. And I'll grab one of those here in just a minute to show you. So back in the day when these were brand new, they're great capacitors. They didn't leak or anything, and they were nice enough to mark the outside foil end of the capacitor by putting a band on it and printing outside foil on it. Now, the outside foil end means that this lead on the capacitor comes into here, and it also attaches to an outside foil jacket that's just right underneath this paper here, and it shields the entire capacitor. So if we were to tie this to the chassis, this whole capacitor would be shielded right up to this point, right to where this lead goes in. This lead goes to the inside layers. So in effect, these capacitors actually do have a polarity. Now, so do a lot of the modern capacitors, and if they're built correctly, they'll actually be made with, metallized polypropylene or, PVC or whatever they're building their new capacitors with, and of course, whichever new style capacitor that you end up buying. They will have an outside foil jacket connected to one end. It's just that they didn't spend the time to actually mark it. And that's what we're going to do in this video, is we're going to locate that outer foil or the outer metallized polypropylene layer, so that when you install your capacitors into circuit, you're going to pick up less hum and a less adjacent interference, and either you're not going to get oscillation because you have a really large exposed surface hooked to a high impedance portion of your circuit. So now, these capacitors, we'll just use this as an example for a modern capacitor. So say this was a brand new modern capacitor, okay? If we were to install this into the circuit, this end here would go to the lower impedance point always. So this end here with the band, if we were to use this as an RF bypassing capacitor, would always go to the chassis, and this would go to the grid of the tube, say the screen grid, if we wanted to keep RF off the screen grid or something like that. It would go like this, because when we tie this end to the chassis, this entire capacitor is shielded right up to this point. Now, if we hook this up in reverse and say we tied this end of the chassis and this end of the tube socket, we'd have all of this area that is completely exposed right up to this point. So, of course, we don't want to have that because that's more exposed area, and of course we're going to pick up more interference that way, especially if we have a filament or a heater line running past this. That's definitely no good. We definitely want this end to the chassis side. Now, when we're hooking this up to a standard audio amplification circuit here, this capacitor would go in this way because the band end, or the outside foil end, always goes to the lower impedance portion of the circuit. And the lower impedance portion of the circuit, most of the time, is the plate of the preceding stage here, or the earlier stage, I should say. So, this band end will always go towards the plate, and this end always goes towards the grid in this particular circuit, and in this capacitor would be the same way, and if we had a capacitor on the input here, it would be the exact same way again. On this bottom circuit here, we'll notice that there is a capacitor missing on the screen grid, and this would be considered an RF bypass capacitor. We want to keep RF off the screen grid here because we don't want this screen grid to amplify any kind of oscillations or any kind of interference that's in the chassis. So by mounting this capacitor in, we would have to mount the band end to the ground or the chassis, and that would tie to the screen grid. Now, of course, we don't want a lot of lead inductance there, so we want to keep the lead as short as possible. But again, you have to use some common sense. You don't want an extremely short lead so that when you're soldering it, if you have a newer capacitor, you're going to melt the metallized polypropylene with the heat of your soldering iron. You'll probably need to leave a little bit of lead so that it'll dissipate some heat. So again, these capacitors need to go in like this, and they need to go in like this, and they need to go in like this. Okay, so depending on what stage or what kind of schematic you've got going on. So now we have new capacitors that look like this right here. You can see this. This has no markings on it. And when these capacitors are created, they're going down the assembly line this way, and then they get the writing or the printing on them this way, or they'll get them on this way because it really doesn't matter. They're in a machine that doesn't really pick which way they go down the line. So they could be any old way, and we need to find out which lead is attached to the outermost metallized polypropylene, or we could call it the actual shielding inside the capacitor, which would be the outer layer, the outermost layer of this capacitor. And that's very important so that we install this into the circuit the correct way, because we don't know. Now, a lot of people think that when they buy these orange dip capacitors that, oh, look, they've been really nice and they've marked that. Well, really, have they? This is how you test for the outside shielded end of your capacitor, or the outside foil end, or outside metallized polypropylene layer, however you want to call it. We're really just looking for the shielded end of your capacitor, and this is how you find it using an oscilloscope and a very simple little setup like this, which is basically just a BNC cable with a center conductor attached to an alligator clip, and the shield is also attached to an alligator clip. I have them right now just clipped together to keep the noise off the screen. So if you have a newer modern DSO that goes down to about 5 millivolts per division, you should be absolutely fine. Right now this is running at 2 millivolts per division, and we're not going to get too accurate with the readings because really I'm just acting as a random hum antenna in order to determine the outside foil end of these capacitors, and I'll explain that here quite shortly. So the first capacitor we're going to look at is this old wax capacitor. Now, we wouldn't want to use this in circuit because this capacitor is well past its due date, but we're really just looking at a shielding aspect of this capacitor, so this will be just fine for this test. So what I'm going to do is I'll hook this into circuit the correct way, and we'll look at the signal on the screen and the amplitude here, and then we'll reverse this capacitor and see the differences. So right now, I'm just connecting this thing up, and this is the way that it should normally be. I'm acting as the hum antenna right now. I'm holding the case of the capacitor right now, so you could look at me as a very nearby heater line running past this capacitor in a chassis or something like that. So that's the amplitude that we got with it hooked up the correct way. You can see the banded end is connected to the outside shield of the cable. This is the lower impedance portion of the circuit. This would be the chassis. And we're always looking for the lowest amplitude. When we have found the lowest amplitude, we have the capacitor hooked up the correct way. When the amplitude's high, it's hooked up backwards. So what I'll do is I'll hook this one up the other way. And we can tell that we have this hooked up backwards because now the outside foil, which is the shielding on this capacitor, is capacitively coupling to me, and I'm feeding signal into my oscilloscope so that we can see here very simply that this capacitor is now hooked up backwards. Remember, we're always looking for the lowest amplitude, and then we know when the negative or the common lead of our oscilloscope is hooked to that end, when we have the lowest amplitude, that is the end that we will mark as the outside shielded end or the outside foil end or whatever you want to call it. So that's this capacitor here. So let's grab a newer orange dip capacitor and take a look at it. So here's a newer orange dip capacitor, and we have a line here, and we might think that, oh, that line indicates the outside foil end. Well, let's test that out. I'll just hook the capacitor up to it right now. It's much easier to hook this up off of screen here. So there we go. So now I've got this outside shield of my braid hooked up to this end. This would be considered the chassis, and this here would be considered the part that goes into the higher impedance portion of the circuit. Okay, so now what I'll do is I'll flip these leads around. Now if I flip these leads around and the amplitude goes down, that means that this side is not the outside foil end. Remember, the side that the shielding is on is always, when the amplitude is lower, is the outside foil end. So what I'll do is I'll reverse these leads right now. And look at that. We have lower amplitude here. So this line here does not denote the outside foil end. This side here is the shielded end of this capacitor. So again, I'll hook this back into circuit the other way, and we can see that we have more amplitude this way. And then if I change these around, you can see that there's almost nothing there. So this side here would be the side that we would want to connect to the chassis. We would mark this side here with a line as the outside foil. Okay, so let's grab another orange dip capacitor right here and test it out the same way. So I'll hook this up the way that we would think that it's hooked up. This is the band end here, so we'd figure that that is the outside foil. Alright, so now what I'll do is I'll reverse the leads. And we can clearly see with this capacitor that this side here is definitely not the outside foil or the outside metallized polypropylene or whatever metallized PVC. This here, this side is. So this here would be considered the shielded end of the capacitor. This is the side that would attach to the chassis. Again, I'll reverse this. And you can very clearly see that this is not the shielded end. So let's test an older capacitor here. I have an older, kind of a burgundy dip. I don't know what you would call this, but let's consider the line end on this one as the outside foil. So I'll just hook this one up now. Okay, so here we go. Alright, you can see the line is on this end and we have the common or the negative lead hooked up here. Alright, now I'll reverse the leads. And we can see on this capacitor, that line does denote the outside shielded end of the capacitor. So on this capacitor, you could regard this line as correct. Now, whether these capacitors are going down the run like this and they're going down the run like this, we don't really know because I don't have more of these to test, but it just so happens on this capacitor that this end here is the shielded end. Okay, so let's take a look at this old General Instruments capacitor. Alright, and let's test it out and see if this band end is the outside foil. So I'll hook this one up the way we would think it would be hooked up properly. Again, we have the band end hooked to the ground, or the common. This would be considered the chassis. Okay. Now I'll reverse it. And we can clearly see that this is not the outside foil end on this capacitor either. So really the bands on the ends really can be considered either way with a lot of these capacitors. So really, you need to test them in order to really know what side is the outside foil. And you can very clearly see that there is a polarity to these capacitors. So I'll grab one of my brown dip ones here. All right, and I'll hold this one. This one has absolutely no markings on it. So we'll test this one out here. You can see this one here. Okay, and I'll reverse the leads. It's just shorting there. I got these leads all twisted up. There we go. So we can clearly see that this end here is the band end right here, even though there are no markings on this capacitor. So you can see the differences there. There's the lower amplitude this way, and I'll reverse the leads. And we can see that we have higher amplitude this way. So this end here is the shielded end. So now what we want to do is, since we're going to be testing these things, we're going to, if you're replacing a whole lot of these things in a radio, you're going to be, basically have a small bag full of these things. So you don't want to be doing this as you're, putting these things in the radio. You kind of want to pre-grade these things and find out which end really is the band end so that you do install these things correctly. Just short these leads out here. So what we're going to do is create a small circuit that does this a little bit easier for us, and we'll check out maybe a couple of different ideas and see what we can design here and make a little test jig for these things. Before I start building a small project, I usually like to check my own stock and see if I have enough parts and pieces to make this with the parts that I have on hand. So I would like to build this into a smaller project box, and it just so happens that I have another one around. I built the TDR out of the same one. I can't find the other project box. I put it in a very safe place so that I would find it the next time, as I can now see. So anyways, I'll locate this other project box. It looks just like this one here, except of course there's nothing in it. It's just a solid cast box here. So I'll end up using this box here, and the reason I want to use this box over a plastic box is this is completely shielded. You got to remember, we have an oscilloscope that's down at about 5 millivolts per division, and maybe even 1 millivolt per division. So if we have a plastic box, a lot of noise is going to get into there from anything that's basically around it. The thing is, any kind of wire length inside this box, if it was plastic, would act as an antenna, and we'd be picking up all sorts of just noise and random garbage. So what we want to do is we want to have everything enclosed in a solid a cast box here. Another thing that we have to think about is, a battery. So I'm going to need to install a battery in here, and I'm most likely going to end up using a 9-volt battery for this. So, it's going to take up a small portion of this box. So I have to locate things inside of this project box so that, this whole thing will work out. I need to put a BNC jack on here. I'll need to put a switch on it somewhere. The battery will have to be mounted in here. There'll have to be a small circuit board in here that all of our parts and pieces are going to be on. And we also have to think, if we're going to say I'm going to have 2 alligator clips sticking out of the top of this box or something like that. All right, now I'm going to also have to have an LED beside each alligator clip so that I know when this thing is moving around like this, when it's reversing the polarity of the capacitor, so that we can note the the amplitude difference on the screen. We're going to have something that's going to mark the side that's the band end. So I'm going to have maybe some rubber grommets, and then maybe some LEDs on the top of the box. So everything has to be taken into account, because we can't push the battery down on top of the LEDs, and we also need space for the wires to come out of the top of the box. So the battery will have to sit over to one side, and this is all stuff that you have to think about before you plan this. So what you do is, of course, you get your box, and you put the battery inside, and you move things around, and you ponder over some things for a little while, and then when you come to thinking, okay, this layout is going to work, then of course you can start building with that layout. So now, in order for this to make testing easier, we obviously need some form of a circuit that's going to take this capacitor, and it's going to reverse it. And of course we don't want any imposed noise from the circuit that it's around. So in order to make a circuit that's going to reverse this, we're going to need something that's going to look like this. So we can look at this as right here, if we were to have the capacitor under test right here. So this is the capacitor under test, okay. And say this here is the scope common, and this is the scope, you know, the center conductor. We'll just put plus here for ease of drawing. Okay, so this is the center conductor of the oscilloscope probe, and this here is the scope probe common. So if we want to have this in the circuit, say this is the negative side of the capacitor here, we're going to need to close this switch, and we're going to need to close this switch in order for the positive probe of our oscilloscope, or the center conductor of the cable, to be attached to this side of the capacitor, which then would make this side here, and then of course this would run to ground. So you can see we have a circuit here now. So then in order to reverse this capacitor, in order to flip it, these two switches would have to open, and then this switch and this switch would have to close, and then of course that would make this side running up to the center conductor here, and then this side here would end up becoming the common side, because this switch is connected to ground. And we're going to also need some form of, say, an LED or something at this point to denote when this side here is the common side, or whether this side here is going to be the common side. So we're going to also need two LEDs to do that. So now we can do this with relays, and of course we're going to have a little bit of current consumption if we do that, and we're going to hear click, 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 click inside this box. Or we can do this with an IC, and I'll probably end up using an IC because there's limited current draw with an IC. There's a bunch of ICs that basically work as single pole, single throw switches. And I'll find something that's rather common to use, and we'll make this particular circuit using a bunch of ICs. Now if we use an IC and it's got a bunch of FETs inside it, we're going to also want to have something on this particular point here, which basically is two diodes like this, one diode like this and one diode like this, and that's going to also limit this basically to about 0.6 or 0.7 of a volt on each side. So just say there's a bit of a charge on that capacitor, say you forgot to discharge it a little bit, or if there's you have static, you're not going to zap this IC if we use an IC. So this is basically just going to protect it and limit the voltage that goes into the circuit. Now of course you would always make sure every single capacitor is discharged before you stick it into circuit, and all this is going to do is protect the IC that these switches are in. And of course we would want the same thing on this particular side here, and it would be exactly like this. So basically all that's doing is this is limiting this input circuit where our capacitor under test is to about 0.7 of a volt. Now keep in mind that we're testing most of this down at around 10, maybe with our amplitude, maybe we're exceeding 50, 60, 70 millivolts with the hum in our that we're imposing into this capacitor. Who knows? But this is going to be up around 600 or 700 millivolts, just about a volt. So this is well beyond our test. So this is just protecting this here. So now what we're going to also need to do is we're going to need to implement some sort of a circuit that's going to close these two and close these two, and then it's going to have to do this, right, in order to flip this capacitor back and forth and back and forth. So we're going to need some sort of a flip-flop, probably a D-type flip-flop or something like that. And then if this is in an IC, these are going to be controlled. So this side here, right, and this side here would go to one leg of the flip-flop, and then this side here, and of course this side here would go to another part of the flip-flop. Now keep in mind that this is just only a rough sketch, and I'm just trying to get the idea across. When it comes to actually designing this, we'll go over to the whiteboard and take a look at it there. So now that we have a flip-flop that's basically just going back and forth like this, when this side is positive, say, we're going to probably not use just a 74HC. We'll probably use a CD 74HC ICs for this because we're dealing with a 9-volt battery. Just 74HC logic is usually only good to between about 5 and 7 volts maximum. So we're going to be using a 9-volt battery, so we're going to be wanting to use parts that start with CD. And of course we'll take a look at the data sheet just to make sure that it will be fine around the 9-volt area. So now that we have this type flip-flop here, now we need also a timer that's going to set out a pulse into this. That's going to tell this to go back and forth like this. So, of course, when this side is high, this side is low, right? And then when this side is high, this side is low. So basically what this is going to do is it's just going to close these two switches, and then close these two switches, and then close these two. So, you know, when these two are closed, these are open, obviously. And it's just going to go back and forth like this. And we also want to set the timing rate of this timer so that when we have this thing on the bench and we're looking at, say, our oscilloscope here, we want it to go slow enough so that when we can see the amplitude change on our oscilloscope, the amplitude goes down and then the amplitude goes up. We want to have a chance when it goes down again to look at the box and note which LED on which side of the box is going to be lit up. So when we know that, you know, the amplitude is low and this LED is lit up, we'll know that this side here would be the band end of the capacitor. So that's what we want to try and do. So these are the parameters that we're basically dealing with. We have a 9-volt battery, so we know that we're going to need like you know, a CD 74HC parts or just CD parts. The 555 timer is good for 9 volts, so we don't really have to worry about that. We'll use a 555 over here, probably a D flip-flop or something like that. And I'll have to figure out some really common part for this, so that way you know, it's easy to put together. Now, if you have a bigger box, you don't need to use a small box like I'm doing. You can build this onto that you know, that proto board stuff, and you can use through-hole ICs. I'll probably end up building this for myself with surface mount stuff, just so that I can fit it right inside this box. And then, you know, this box will have a BNC come off of it, and then a power switch, and it'll probably have 2 little alligator clips. Now, the cables that are going to come out of this box, I want to be shielded right up to the alligator clips, because you know, if we have just 2 long wires sticking out of here, those are really acting as 2 antennas. So the more shielding we can get right up to the alligator clips, the better. So I'll have 2 small shielded pieces of coax coming up here, and of course we want, you know, a little bit of lead length so we can move them around. If we have, you know, a large axial capacitor, we can clip them onto the ends, or if we have one of the newer style ones, I'll grab this one here. We have one of the newer style ones like this, you know, we can just, you know, put the 2 leads together and clip them in like this. So the whole idea is to make this thing functional, especially if you're going through all sorts of different types of capacitors. You know, we want this thing to be about just as versatile as we can make it. So now that we have the plan here, I'll figure out an actual circuit, and I'll draw it up, and we'll head on over to the whiteboard and I'll explain it there. This is the circuit I've designed for our little capacitor test jig. So I ended up using a CD74HC4066 to flip the capacitor around in circuit. Now this is an IC, and it's a CD74HC4066. It's not just a 74HC4066, and the reason that I used this one is that it will go up to 10 volts. Remember that we need to keep the supply voltage of our ICs well within a safe zone. I'm using a 9-volt battery over here to power this, and again, this is all just due to size constraints. I have that little aluminum box, or that little cast box that I showed you, that I'm going to end up fitting this all in. If it's around here somewhere, I still haven't found it, but I'll fit all that into that box. Again, you know, you can build this into any kind of size box. If you have a larger aluminum box, you can, you know, of course, use a different kind of battery style power source for this. You know, a bunch of AA batteries or whatever fits in that box. Just keep in mind that the box has to be either solid metal or solid aluminum or a cast box, some sort of conductive box, because again, our oscilloscope is running down, you know, between 1 and 5 millivolts. It's going to pick up any kind of noise. No power supplies running into this thing at all. It should be battery powered. So we'll get back to the circuit. I've drawn this IC the same way that you would kind of look at relays, just to make it a little bit easier to understand. So how this IC works is really quite simple. It really is just 4 switches inside of one IC. So pin 13, pin 5, pin 12, and pin 6 are the control pins. So if, say, pin 13 goes high, that'll connect pin 2 and pin 1. So technically it just closes the switch inside. So pin 13 and pin 6 are tied together, pin 12 and pin 3 are tied together, so basically it's just closing the switches like this. And this is all done within an IC. There's very low current consumption, you don't get the clicking from a relay, and you know, it's a real consistent test, because we're using FETs inside this in order to switch this in circuit. Now, there will be a little bit of resistance in the switch, and I'll explain that in a little bit. It's between 15 and 20 ohms, but that's absolutely fine for testing these capacitors. There'll be no issues with this whatsoever. So this was a really good solution. The CD74HC4066 is a really common part. It's an off-the-shelf part. You should be able to find that with no problems. Again, you can build this through hole. You don't need to build this surface mount. The only reason I'm building this surface mount is because of my little box. It's hiding here somewhere, and I'll put all this stuff inside that little box. So these are BAV99s. These are just, they're two diodes in one SOT23 package. You don't need to use the BAV99. You can use a 1N4152 or a 1N914, or if you think you're going to be crazy and leave a capacitor charge and stuff it into the circuit, you can use a 1N4007s or whatever you want to use. Remember, this is just working at a really low frequency. You're coupling the 60 cycle signal in from your body, really, and inducing hum into the circuit so that you can see which end is the shielded end. So really not too picky. So I use the BAV99s just because they fit on the little circuit board quite nicely. So, and I'll get into this here in a little bit. I've already got the little circuit board already pre-drawn and ready to go, and we'll get into that next. I'll show you how I've drawn that up. So that's one of the reasons that I use these. They fit on there really quite nicely. So now here I've got a CD4013, which is a flip-flop. It's a D-style flip-flop. And what this really does is when it receives a pulse in pin 11 of this IC, what it does is it just basically, this pin will go high, this will go low, and then it'll receive another pulse and it turns the other way, and it just keeps going back and forth like this. Now you can see I've got two really high brightness LEDs here, and the reason that they're high brightness is because I'm using a 22K to ground resistor, and you can use one or two, it really doesn't matter. The reason I'm using this is because they pull very, very low current and they're still pretty bright at that point. So I don't want to use up my battery power lighting LEDs. You got to remember, in this circuit, one LED will always be on. It's just going back and forth. So when this side here goes high, this LED will glow. Now this LED here should be positioned by the negative part of the switch. So pin 8 and pin 9, where pin 4 and pin 8 run out to your alligator clip, that's where this LED should be located. All right, so where this LED should be located should be close to pin 1 and pin 11. So what's going to happen is when this side goes high, it closes this switch, and what that's doing is that's bringing this side of the capacitor to ground. And remember that we're looking for the negative side of the capacitor, or the shielded side of the capacitor. And you want this LED close to this side, you want the red LED close to this side. So when this side goes high, this one here is pulling this side of the capacitor to ground. Again, we're looking for the shielded side of the capacitor. If you have the LEDs reversed, you'll end up marking the wrong side of your capacitor. And I'll show you how to test for that in the end to make sure that you have the LED on the right end, just in case that's a little bit confusing. Again, we have a pulse going into pin 11 here. So again, this is just going like this, and you can see the action with the LEDs. You'll see the LEDs move back and forth. This is a 555 timer. And what this little 555 timer is doing is just creating the pulses in order to tell this flip-flop to do its flip-flopping. So it's just going to keep it doing this. Now I chose a 180K resistor and a 1K resistor because I find that to be a very nice balance. You don't want this to go too fast because you're not going to be able to look at the screen and then really quickly look down to the box and then see which LED's lit and mark the line on it, right? You want enough time so that when you see the amplitude go small, you can look at the box, see which LED's lit, and draw a line on, and then by that time it's already back over to the other side again. And I'll explain all this in the end, and you'll see how this actually functions. So you can speed this up if you want. If you find that this is a little bit too slow, and you want to be Superman as you're grading all your capacitors and you're just hammering them through really quick, you can change this 180K resistor down to 150K, and it's going to go quicker. 120K, and you're really working. All right. If you find that 180K is too fast, up it to 220, and you'll have plenty of time to sit there and have a sleep between the LEDs as they're switching back and forth. Okay, so this 180K resistor, you can put a VR in there. Again, I'm keeping it simple. I'm dealing with size constraint because of that little box that I've got. So I just want this thing, basically you turn on a switch and the thing just starts doing its action and I can grade cap. So it's just a happy medium. So 180K and 1K work very well. I'm using a 22 mic tantalum capacitor down here, and the reason I'm using a 22 mic tantalum capacitor is because I have a lot of them. So that's really the only reason. There's a 0.01 cap coming off of 5 just to keep noise out of the 555. You'll see here that these are all the supply lines for all the ICs. We have pin 14 and pin 14, pin 7 and pin 7 for both of these ICs, and 4, 8, and 1 for the 555. So 14, 14, 4, and 8 are all positive, so 4 and 8, and this is pin 14, and there's a pin 14 on this that also has to be tied to positive. And we have pin 7, and pin 1, so there's a pin 7 on this IC that has to go to ground. There is a pin 7 on this IC, as we can see here, that goes to ground, and then we have pin 1 here going to ground, and that's really just the supply. Again, you can put the switch in the positive or the negative side, absolutely fine. Whatever you think will work just fine for you. So I've got a 22 mic cap on the supply here, just to keep noise out of the circuit when this thing is switching. What else can I tell you here? I think that's pretty much it. This will draw between 3 to 8 milliamps, somewhere in there, depending on the ICs and the manufacturer and everything. That's really quite nice. If you use relays, you're going to end up with quite a bit more current consumption. So that was the whole idea of using a 9-volt battery and a bunch of ICs. We can, we'll get a really long life out of this little switch. So everything should work just fine. Scope common goes to pin 10 and pin 9. So basically pin 9 and pin 10 of the 4066 will just tie to the chassis or to the box. And then the BNC center that you have coming that goes right out into your oscilloscope will tie right to pin 2 and pin 3. So and then of course that's a continual, and then this isn't moving. This is your scope hot and your scope common. There's nothing moving there. That stays there. And then of course the switching is going to do its switching at that point inside the IC and flip that capacitor around as this 555 timer is telling this flip-flop to go back and forth. And that's pretty much it. So what I'll do is I'll take you over to the computer now, and I'll show you the little layout that I've got designed up, and it's a surface mount layout. Again, you don't have to do it surface mount. You can build it through hole or however you want to build this. You can build it dead bug style, whatever works for you. So let's head on over to the computer. This is the surface mount version circuit board that I've come up with for this little capacitor tester. So this is really quite blown up. This is a really small circuit board, but I've just enhanced it so that it's easier to see on camera here. So this is the top layer. The green layer is the top, and the black is the back side of the circuit board. So this is a double-sided circuit board. This little IC here is the 555 timer. This is pin 1. This is the timing cap, that 22 microfarad tantalum here. These are 0402 parts. This is the 180K resistor. This is the 1K resistor, and this is the 0.01 microfarad capacitor off pin 5. This here is the other 22 microfarad tantalum that's across the supply. This here is the CD4013, which is the flip-flop. And this is the 4066 over here, the CD74HC4066. This is what's going to be doing our switching here. These here are the screws where it mounts to the chassis of that little aluminum or a cast box that I've got. These are the resistors that's on the back side. This resistor is a 22K resistor, and this is the LED. This LED correlates to this side. This is the test lead that runs out this side. This is the center conductor, and I will solder the shield or the braid of that little piece of coax to this piece of the circuit board here. And then, of course, we want the LED close to that rubber grommet where the test lead runs out. And it's the same for this side. This is where the center conductor of our test lead runs up to the alligator clip. The shield of the coax will solder to here, and this LED correlates with this side. So these are the high brightness LEDs here. These are 1206 parts here. These are two 22K resistors. This is where the supply or 9-volt supply runs in right here. And this is where the BNC signal runs out. This goes to the BNC jack on the box, and it goes out to our oscilloscope from this little point here. And that's really how this works. So this is really quite small, and I'll show you exactly how this is going to go together here in the next shot. Here is the completed little capacitor testing box here. We can see that I've got my alligator clips fastened to some shielded coax. This is some Teflon coax here. The shielding runs up to about this point here and about this point here. You don't need to use Teflon coax. You can use any kind of coax you want. I just have a bunch of this stuff around. I've put some heat shrink on the ends here just to stiffen things up where the center conductor runs out to the alligator clip, because you know we're going to be moving this around and moving it in and out of circuit quite a bit, and I want to get some longevity out of this without having the connections break. Now of course nothing sticks to Teflon very well, so I've left a little bit of braid exposed, and this heat shrink here has a little bit of glue inside of it so it sticks to the braid quite nicely. And we see the corresponding LED for this wire here and the corresponding LED for this wire here. When this LED is lit, this one here is tied to ground, and when this LED is lit, this side here is tied to ground, so we know which end to mark our band on. These are two little rubber grommets here that I've put in. This is the BNC jack here that will run out to the oscilloscope, and there's a bunch of screws here that just hold the circuit board in, and this is the on and off switch on the side. So on the bottom half, you can see here I've got a little 9-volt battery stuck in there, and there's a little piece of butyl tape that's just holding it in. This is the circuit board that I've built, and this is the little switch in the negative lead. I'll just zoom into this here so we can take a little closer look at the surface mount stuff. So you can see the ICs here. That's the little 555 timer. That's the 4066 down in there, and that's the 4013 flip-flop. And that's the little tantalum capacitor, the timing cap, and so on and so forth, just like on the layout. Those are all the little 0402 parts right down there, the 180K, the 1K, and the 0.01 mic capacitor. You can see how I've soldered the braid of the coax right to the circuit board here, and then the center conductor runs up to this little spot. This little SOT23 package part here is that BAV99 diode. That's just protection so I don't zap the IC in there. And it's the same on this end. I soldered them in sideways because if I ever need to replace them, they'll be pretty easy to get out this way and put back in. Again, you can use a 1N4007 or a 914 or anything like that. You know, it's again we're dealing with 60 cycle frequency here, so there's nothing that needs to be too incredibly fast. See, what else can I tell you? Those are the LEDs that are soldered in. You'll see that there's a space between the circuit board here and the actual case, and that's because there's parts on the back side of the circuit board, and there's also soldering on there. So when I put the bottom portion of the box together here, I had to cut this out on the corner here and on this corner because the circuit board goes, very close to the corner here, and they've got this kind of extruded lip that runs all the way around the entire box here. So there's enough space between the back side of the circuit board and the case to leave this strip in here. It just goes between the circuit board and the case. You can see here's the circuit board that will go right in between here. And that's pretty much the box. So when we turn the thing on, this is about the speed that it runs at with the 180K resistor here. You can see how fast that moves back and forth. So that gives us enough time to mark our capacitor and, of course, look at the screen and then, load a new capacitor. I think that's about a nice, comfortable speed for grading these capacitors. So next, let's hook this thing up to an oscilloscope and see how it works. We're ready to check the polarity of some capacitors in our test jig. So I've got the oscilloscope set to 5 millivolts per division. I've got the alligator clip shorted here, and I'll plug this in and I'll show you that it's a relatively quiet circuit. You can see how quiet that is right now. Now, you got to keep in mind that through this IC, when this side is grounded, it's about 17 ohms to ground, and then when this side is on, it's 17 ohms to ground. So we have two 17 or around that ohm paths, one from positive and one to ground. And that's just the basically the resistance imposed by the IC itself. So even though we still have this, we're going to still pick up noise from the oscilloscope if we bring it close to it and everything. But, for this actual test, this is absolutely fine. And for this little test jig, it's fine. So when we open these alligator clips, we're going to see lots of noise on the screen. And that's absolutely normal because these are acting as antennas. And this is actually just picking up noise from the scope itself even. You can see the amount of noise that comes in from the CRT. So when we put the capacitor in here under test, it actually acts as a filter across the circuit itself, so there is no problem with the amount of noise that we see. So what we'll do now is we'll put a capacitor in here. Let's take this orange dip capacitor and test it out and mark the band end. So here we have me being the 60 cycle antenna again, and you can see the difference in amplitude here as it's switching. So we see this LED is on and the amplitude is lower, so this is the band end. You see, so now that we see this LED on, we would mark this end as the band. Remember, we're always looking for the lowest amplitude. So I'll take my felt marker and I'll put a little line on this end, and I'll know that that now would be the lower impedance portion of the circuit. This would go to the chassis, or this side would go to the plate side if we have this in an amplifier. Again, we can see that this side has a band on it, but we can see that it doesn't really mean anything, you know, according to the outside shielding or anything. This might be some sort of coating that they've put on, or I don't know what they're doing and why they've put this on this one end. But this side here, you know, clearly denotes the outside foil or the outside metallized polypropylene or metallized PVC layer. Okay, so there's one. So we've marked this one. And you can see the speed is comfortable so that, you know, it's, you know, you're not losing control of what you're doing. So I'll put this one in. All right, and I'll put my fingers on here. All right, so we know that this end is the band end also. Okay, so I'll mark this as the band end. Now, if you don't want to leave your felt marker on there, you know, you can use an ink that will easily come off. I find that, you know, a little bit of alcohol will just remove these lines, even if it is one of these Sharpies. So, you know, a lot of people don't want that line on the capacitor when it's in circuit. I've kind of learned to live with it. I kind of like to have the capacitors clean myself, but that's fine. For underneath the chassis, I'm now just beginning to leave the lines on, like you will end up seeing in most of my videos. So this one here, this side here, this opposite side here, this one on this side is the band end where I've drawn that little black line. So let's test another one. So we can see that the opposite end on this capacitor is the band end. So this end is the band end on this capacitor. So you can see there really is no rhyme or reason for these capacitors. You know, they're just kind of going down the line any old way. They're the same capacitor, and they're just printing the labeling on any side there. So it really is important to mark that off. Let's test out this one here and check out its band end. Okay, is that in the shot there? It is. Okay, I'll put my fingers on here. Okay, so this end is the band end right here. So now we would mark this end as the band end. And that's just how simple it is to grade and check your capacitors so you know that you're putting them in circuit the correct way. And that's how this little fixture works. So what we're going to end up doing next is I'll show you how to measure which end is actually supposed to be the negative end, so that you have your LEDs corresponding to the correct lead, just in case you did find that a little bit confusing. Alright, this is how we tell how we've got the right LED on the right lead. So this is the lead here that we're going to test, and we want to know if this LED is corresponding to this connecting to ground. So we've got our meter on ohms, and we have our lead going into the alligator clip here. And you can see that it's 17 ohms when this LED comes on. See that? So we know that this end is connecting to ground, and we have our polarity right. So what I'll do now is I'll move this over to this side, and you'll see roughly the same measurement on this side. See the LED there and the little lamp. Alright, it's me trying to get a good ground on the box here. There we go. So that's how you tell. So if you wire your LEDs up and you have them backwards, if you leave some lead length, you can just swap them around if you don't build a circuit board or something like that. And that's how you tell that you've got the LED connected to the right side. Well, we've come to the end of another video. I hope you find this little circuit useful, and I hope you enjoyed the video. If you did, give it a big thumbs up and hang around. I'll try to make more videos just like this in the very near future. Take care. Bye for now.